Welcome everybody to the CAM Colloquium for this Friday. We're very happy this week to have Wen Sun here from all the way over in Gates Hall. Wen's a relatively new faculty member in the computer science department here. He joined in fall of 2020, so a little over a year now. Wen's part work is in reinforcement learning, and reinforcement learning from many perspectives and all kinds of things. So today he's going to talk about generalization and robustness in offline reinforcement learning. Wen, go for it.
Thanks, Anil. Hello, everyone. It's great to see everyone in person. So I'm going to talk about RL today. And before we start, I want to give thanks to my co-authors, Masatoshi, Jonathan, Drew, all of them Cornell CS graduate students, and Rahul, who's a research scientist at Amazon. And special shout out to Masatoshi and Jonathan, who are the two main leading authors of the papers that I'm going to present today. Great. So I will say that the lessons that we learned from the empirical successful story about reinforcement learning is that when we combine rich function approximation and reinforcement learning together, at the condition where we have a large amount of data, they often can work extremely well. Right? So these examples have already demonstrated that whenever they work, they actually give us something that is way better what we can handcraft or what we can find by traditional search algorithms. So in this talk, we're going to focus on the rich function approximation plus RL setting as well. And before we dive into the details, let's just look at the traditional reinforcement learning paradigm. So the traditional reinforcement learning focuses on the online interaction setting. So as you can see here, there's a closed loop. Right, so you have some RL component that is interacting with this environment. In this case, it's a robot manipulator. And you interact with this environment and you collect the data. And you often start from scratch in the sense that the data set contains 0 samples. Right, so you interact, collect data, refine the policy, and collect more data, and so on and so forth. So this is the very traditional setting. And it is classic, but it may have some drawbacks. For instance, the data collection process might be slow because you actually have to interact with the environment, right? You have to wait for the robot to finish the task to get a new fresh batch. And in a fixed amount of time, you may not have sufficient data, right? And the second point is also important. You have to do some sort of random exploration or random experimentation, right? So if you start from scratch, you have to do some random exploration. And maybe for applications where safety is important, we cannot do random exploration, right? So doing random experimentation may be just not safe at all. So then we come to this offline reinforcement learning paradigm. So this looks similar to the one that I showed before, except that here I deleted one edge, so now it's not a closed loop. So, and instead of starting from a data set that contains 0 training examples, here, I'm going to start from a data set that contains examples, samples, pre-collected from some behavior policy. So maybe you have been using some strategy to interact with the environment in the history, and then I just record down this data and store them in the disk, and then I can use it whenever later on I want to optimize my policy. Right? So we're going to start from a data set that collected by some different policies, and then we want to use this data set to find a good policy so that we can deploy. So the potential advantage of this setting is that, first of all, we might be able to leverage a large pre-collected data set. So we put ourselves a little bit closer to today's supervised learning, right, where we can use big data. 2, just by the nature of this setting, we're not going to do random exploration, right? So we hope that the data set contains useful information, and from there, we might be able to just learn a good policy without doing any experimentation in the real environment. So this, compared to the previous procedure, this is a safer option, especially for applications where safety is actually quite important. So let's look at some applications of offline reinforcement learning. So the first example here is the robotics manipulation example. So in this paper, what they did is that they built a farm of robot arms, and they just let the robot collect and manipulate objects in their beams, and they just do it, let the robot do it for a couple of hours or a couple of days, and then they collect a huge data set. Right? And now you can use this data set to learn strategies to manipulate potentially different but similar objects in the future. The second application is autonomous driving. Maybe if you're a Tesla driver, you're probably going to contribute your data to Tesla, right? So we're going to collect a huge amount of data collected from different drivers driving their car. The third example, which is really interesting, because this is a new work from a recent Nature paper, where they're trying to use offline reinforcement learning technique to do this bloom navigation problem. So here the goal is to navigate this bloom by leveraging the wind field. So your offline data contains the history of wind field in this location, and data corresponding to the movement or the dynamics of the bloom in the history. Now you want to learn a good control strategy so that you can control this bloom by leveraging the wind field in your energy or cost efficient manner. And so this is really exciting. This is real world application of offline reinforcement learning. And of course, there are a bunch of healthcare related applications. Since I'm not familiar with these applications, I'm not going to dive into the details of them. But for those of you who are interested in these healthcare applications, you actually can read this fantastic offline reinforcement learning survey from people at Berkeley, where they actually talk about the healthcare applications where people are actually using reinforcement learning, specifically offline reinforcement learning techniques to solve the problem. Right. So offline RLU is promising, but it is also challenging. Right? So the reason is that we just don't have the ability to interact with the real environment anymore. So this forces us to do some sort of counterfactual reasoning, right? So we're trying to figure out what would happen if I apply something that is different from the strategy that I used to collect the data. And to see why this is challenging, that's actually just contrasted against the supervised learning framework. Right? So in supervised learning, we're given a huge data set. So this is the ImageNet data set. And with that data set, we just fit some rich function approximator. For instance, in this case, I fit a nonlinear function approximator, which allows me to do prediction for test examples. Right? So in the test time, I have these examples coming one by one, and I make a prediction. And the key property of supervised learning is that there's no mismatch between training distribution and test distribution. Right? So after all, the supervised learning paradigm is operated under the assumption that the test data is also ID sample from the same distribution where we collect the training example. So in other words, the inference procedure in supervised learning is passive. No matter how good or how bad your prediction is, it's not going to really affect the future test example you're going to see, right? Because after all, we're assuming everything is ID sample from the same fixed distribution. But this is fundamentally different in reinforcement learning and in offline RL. Right? So there, we're actually going to face this issue called distribution shift or covariance shift. So in this cartoon example, I collected an offline data set that consists of perfect expert demonstration about driving this car on this track. Right? I run my favorite maybe reinforcement learning or supervised learning algorithm to try to learn a good driving strategy from this data set. And this might be the trajectory that I'm going to see during the test time. Right? So in the test time, I'm going to execute the driving strategy that I just learned. And due to some small mistakes that I'm going to make, the mistake might going to compound in the future. And gradually I'm going to deviate from the perfect expert demonstration. And at regions where the deviation is large, I basically have no idea what to do because I have never seen any data in that region. Right? So this is fundamentally different from supervised learning because here, your prediction affects the future distribution of the states. Where in supervised learning, you're passive. You don't have the control on the distribution. Right? So fundamentally, you're going to see this distribution shift in reinforcement learning. That's why reinforcement learning is much harder than traditional supervised learning. Okay, so hopefully I've convinced you that offline reinforcement learning is promising and it's also challenging. And in this talk, we're going to mainly look into this high-level question. So how should we tackle offline reinforcement learning from scratch? Starting from even the formal setting and defining the goals for offline reinforcement learning to designing algorithms. And particularly, we're interested in the setting where the offline data that we have does not have sufficient coverage. Like just we saw from the previous slide, maybe the offline data is only covering small part of the state space. So what we can do there. Okay, so in terms of the outline for today, for the first part, let's together rethink the goal of offline RL. So particularly, I want to mention two properties, robustness and generalization. So we will get there in a second. And then the second part of this talk, let's see if we can achieve this goal. And the third part of this talk, let's talk about special setting of offline reinforcement learning, where we have some additional expert demonstration together with the offline data. So let's do some offline imitation learning there. Okay, so now I'm going to jump into some definitions. So the first definition is the Markov Decision Process. So this is the framework that we're going to stick to throughout this talk. So in MDPs, there are two components, the learning agent and an environment. So in the agent's mind, she has something called a policy, which is a maps from state to action. So here, state is a description of the current status of the environment. And once the environment receives the action, it will send a one-step immediate reward back to the agent. So this is the one-step immediate reward of the current state and the action. And it will also send the next state, S prime, back to the agent. And here, S prime is sampled from this unknown Markovian transition. So this is Markovian because S prime is independent of the history, conditioning on the current state and action. Right, so this loop goes on for capital H many steps. And our goal is to optimize the following objective function, which is the expected total reward across this H many steps. And our goal is to optimize this objective function with respect to our policy. So that's the general setting for Markov Decision Process. And now let's talk about the offline data collection procedure. So let's imagine that I have some behavior policy that has already interacted with this environment many, many times in the history. And my offline data will basically be collected from these interactions between the behavior policy and the environment. So let's abstract things a little bit. Let me just introduce this distribution definition. So this is the induced state action distribution of my behavior policy. So the detailed definition doesn't really matter too much. So here, think about this distribution is sort of telling you, what's the probability of this behavior policy visiting that particular state action pair. Right? So given the policy, we have a distribution over state action pair. And what we can assume is that we have this offline data in the format of state action next state triples, where the state action part is ID sampled from this behavior policy's induced state action distribution. And the next state is sampled from the unknown ground truth transition, Markovian transition.
I'm sorry,
Yeah.
Are you looking at deterministic policies?
It doesn't matter. It could be stochastic, or it could be deterministic, because the environment is in general stochastic.
So that's why it's on S cross A.
Yeah.
Okay, got it.
So for simplicity, let's just assume the policy is stochastic as well. Because in the offline data, I might want to do a little bit random exploration, right? Because otherwise, there's literally no hope to do counterfactual reasoning. Okay. So this is setting. And again, these triples, let's assume they are RID. This is just for analysis simplicity. We might be able to extend whatever we're going to talk about to a long sequence of Markov chain, and as long as that chain makes pretty fast. Right? But let's not talk about mixing in this talk. Good. Okay, let's look at this cartoon example. Right, so here I'm abstracting this state action pair into this x-axis. And the y-axis represents the density or the likelihood of this distribution. So this blue curve is representing the induced state action distribution of my behavior policy. Okay, so as you can see here, the behavior policy is kind of diverse, but it's not really covering the entire state action space. And what happens if my optimal policy, the global optimal policy's distribution, actually has a disjoint support with respect to the offline distribution? So in this case, there seems very little hope for us to find pi star by just leveraging the offline distribution, right? Because after all, they don't even have joint support at all. By looking at the offline data does not tell me anything about the behavior of the optimal policy, the global optimal policy. So maybe in this case, we should switch our goal. And it is possible that my offline data has already covered a large family of policies. Maybe in this case, pi 1, pi 2, pi 3, and maybe one of them is actually pretty good in the sense that it is not necessarily the global optimal, but it might be the second best one that is close to the optimal one. So in this case, maybe our new goal here is to say, can we actually find the best one among those that are actually covered by the offline data? Right? So that seems a reasonable objective that we should shoot for. And this is what I call robustness, in the sense that as long as there is a high quality policy that is covered by the offline data, we want to find it. Right? And in the ideal case, when the optimal policy is covered by the data, then we will find it under this condition. Okay, so let's look at this particular example. Let me just make things a little bit more concrete. So this is a very simple binary tree Markov decision process. So I have two actions at every node, left and right. The transition is deterministic here. And if I take action left, I go to the left subtree. Take action right, I go to the right subtree. Right? Super simple binary tree Markov decision process. I have reward 0 everywhere except 2 states. I have a golden state at the end of the rightmost path. The state 15 has reward 1. And the state 10 has reward 0.9. The rest of the states have reward 0. So obviously the optimal policy will choose the rightmost path. Right? It will hit the golden state, collect reward 1, and the optimal policy will be happy. Now let's say that I have some offline data that covers the left subtree. Right? I have a lot of offline data. They all cover the left subtree, but somehow the offline distribution has 0 support on the right subtree. So in this case, there is still a high quality policy indicated by this green path is covered by the offline data. Right? So in this case, there's little hope for us to identify pi star because we don't know anything about the right subtree. But if we can find this green path, then we are happy too because it's not too bad. And in the ideal case, when the optimal trajectory falls into this green subtree, then we will find it too, right? So more abstractly, maybe we want to compete against whatever is covered by the offline data. Right? And if there is a high quality one, let's find it. Yes?
So if pi tilde is the optimal policy in the support of this offline data that we have, is there a reason that it's not taking us to 11 rather than 10?
Oh yeah, so 10 has reward 0.9 and 15 has reward 1, other states has reward 0.
Oh, I see. Thank you.
So in this tree, only 2 states has reward.
Okay.
So I'm going to use this example over and over again. So basically you have the best policy getting reward 1, second best getting reward 0.9. The rest is 0.
Okay, I was mistaking the labels on the leaf nodes for the rewards associated with them. My bad.
Oh, sorry, yeah.
So
Yes.
I guess you're gonna cover this later, but so you haven't yet defined what covered is.
Yes, I haven't. Yes,
Okay,
we will get there. Yeah.
It does seem like, if I think about what you were saying about costs earlier, you would need some minimum sort of boundedness or compactness to say anything. Like, I cannot observe certain paths which stochastically, like, in certain states I may read somewhere where I have a huge negative cost, it's just not in my data.
So I guess,
Like, if you allow for unbounded costs, it feels like
oh, you mean the
there's
cost
no
function?
definition of covered which would work.
So the definition of the coverage I'm going to talk about actually has nothing to do with cost. So maybe when we get there, let's see if that clarifies your question. Okay, yeah, I haven't talked about what's the formal definition of coverage. We're going to give several examples for defining the coverage in a second. Okay, so that is the robustness. We will revisit that more formally. But now let's switch to generalization. And to talk about generalization, let's revisit supervised learning one more time. Right, so in supervised learning, again, I train a function approximator. And my hope is that the function approximator can predict well on unseen test examples, right? Examples that are not from the training data. And we do that by using rich function approximators like Gaussian process, distributed trees, kernels, and these days deep neural nets. And we can actually learn a reasonably good function approximator as a predictor using finite number of samples. So in other words, in order to learn a good dog and a cat classifier, we don't need to see every possible unique dog and a cat image in the world in order to build a good classifier, right? We just see finite number of samples, and then we generalize. So more formally, for those of you who have seen learning theory for traditional supervised learning, the statistical complexity, the sample complexity of learning a good predictor is often depending on the statistical complexities of the function class you use. So it could be a VC dimension if you're doing classification, it could be random complexity if you're doing regression, or in general it could be covering number, for instance. Right? Or more recently, there are special complexity measures for deep neural nets. But the bottom line here is that, as I said, we don't need to memorize or enumerate all possible unique images of a dog and a cat in this world in order to build this classifier. Right? So we don't have polynomial dependence on the number of unique images in the world. We generalize via function approximation. And that is what we want in RL and offline RL as well, right? Imagine that you want to train a policy for playing Go because the total number of board positions in Go is larger than the total number of atoms in this universe. There's no way for us to visit every possible board position and memorize it, right? So we have to use function approximation to get generalization in the sense that we want to do well even on states or board positions that we never see in the training data. So more formally, I want to identify a high quality policy using this offline data, but probably with number of offline samples scaling with respect to the complexity of my function class rather than the total number of border positions in Go. And so that's what I meant by generalization. So to summarize, so in high level, we want to get a generalization via rich function approximation, and we want to get robustness whenever the offline data does not have sufficient coverage. And the question that we want to answer is that can we compete against the best policy among those that are covered by our offline distribution? And can we do that with number of samples scaling polynomially with respect to the complexity of my hypothesis class, my function class? Definitely no polynomial dependence on the cardinality of the state space or action space. Okay, so that leads us to the second component of this talk. So to see if we can achieve this goal, in this talk, I'm going to focus on model-based learning perspective. So let me describe the setting for model-based approach. So So we have this unknown ground truth Markovian transition, P star. So this is something that we want to capture. And because we're potentially operating in large-scale Markov decision process, so we want to capture that using function approximation. So in this case, maybe I'm using deep neural nets generative models to capture this P star. So every function approximator in my function class is a neural network that takes the state action pair as input and outputs a distribution over the next state. Right? So I have a family of them. I don't know which one is closest to the P star, but I want to find it. For simplicity, let's assume this realizability condition in the sense that my function class is rich enough to capture the ground truths. So this can be relaxed a little bit, but agnostic learning in RL itself is extremely challenging problem. So let's just stick to the realizability assumption here. So this is essentially saying that my function class is rich, such that one of the functions in the class is a good approximation of P star. But of course, I don't know which one it is. My job is to find it, for instance. The second assumption is, let's assume that we have an access to an optimal planner. So in this optimal planner, I take a Markov transition as input, P, and I take a reward function as input. It outputs a policy that optimizes the reward, the long-term reward, under the given transition. Now this is a very strong assumption in computation perspective, right? Because planning itself is a super hard problem. But for now, let's put computation aside a little bit. Let's focus on the statistical aspects of offline reinforcement. So let me emphasize one more time. This is a computation article. In order to compute the optimal policy, I don't need the real world samples, right? Because this transition P is given. So I just needed to do offline computation. Yes, it is a very hard problem, but let's put computation aside. Let's first look into statistical solutions. You know, if you cannot do things statistically efficient, there's no way we can do it computation efficient as well.
So maybe
Yeah.
this, so I think this may be a pedantic point, but you are assuming the state space is known.
Assuming what?
Like when you're assuming realizability, you're implicitly assuming the state space is known. So you cannot sort of visit a state which you didn't know didn't exist.
So you're saying that the realizability assumption implies the state is known?
Just the state space is known. You know every state that you could potentially visit.
Sure. Yeah. Yeah. Okay, so let's look at this naive approach. So this is called certainty equivalence. This is a very simple approach. Let me describe it for you. So the first step, let's fit a model using our offline data. And let's see we pick maximum likelihood estimator. Right? So this is a supervised learning article. I'm searching for a model over my function class that fits the training data best in terms of maximizing the data's likelihood. So this is supervised learning article. Maybe use your favorite stochastic gradient update procedure to find one. Right? So let's see we find one. The second step is that let's just treat that as if it were the ground truth model and take the known reward and call the optimal planner to find the policy. So let's denote that as pi hat. So if p hat is equal to p star, then we know that pi hat will be equal to pi star. But the problem here is that my offline data might not have sufficient coverage in the sense that my p hat might not be close to p star at some region of the state space. All right, so to illustrate the problem, let's look at this toy problem one more time. Again, this is a binary tree Markov decision process. I have reward only at two states, reward 0.9 at state 10, and golden state 15 that has reward 1, and reward 0 everywhere else. I have offline data cover the left subtree. Let's just assume we have tons of offline data, so everything inside this left subtree is known to us, basically. But everything outside of this left subtree, we've seen 0 data, which means that the learned model p hat could really be arbitrary on the right subtree because it just doesn't have any data to support its claim. Right? So let's see that p hat completely mess up the transition at state 3. So by mess up, I mean it completely misunderstands the meaning of the action. So p hat believes that if you take action left, you will actually be routed to the right subtree rooted at the node 7. And if you take action right, you will be routed to the left subtree. So it completely misunderstanding the meaning of the left and right. Right? And then again, this could happen for p hat because it doesn't have data to support or disprove its claim, right? Now this is kind of bad because now if you do the optimal planner inside this p hat under the given reward function, you're going to find a policy that takes the sequence of actions right, left, right. Right? Because if you take action left at node 3, p hat believes that it will route you to root 7, which will allow you to hit the golden state afterwards. But the reality is that if you execute this right, left, right sequence in p star, you will miss the golden state, right? Because you will be routed to node 6 instead of 7. So in real p star, when you execute pi hat, not only you miss the golden state, but in this case, because you took the action right at the root, you're also going to miss the second best trajectory that is covered by the offline data. That seems not that nice, right? Because I give you a huge amount of offline data that covers the left subtree, but yet you cannot find the best that is covered by this huge amount of offline data. Something seems wrong here. Okay, so now let's see how we can fix this problem. So I'm going to introduce some conservativeness by some constraint optimization. So in this approach, the first step is still the same. I'm going to learn a maximum likelihood estimator using MLE again. So this is my p hat. And now I'm going to do this constraint conservative policy optimization. Okay, so this objective function involves max and mean. This looks kind of complicated, but let's interpret one by one. Let's look at the constraint first. You know about the max and the mean objective function for now. Let's just look at the constraint. So the constraint is actually measuring the divergence between a function p with respect to p star averaged over the training data. So let's abstract this as a distance metric between p and p hat. This is almost a valid metric in the sense that it satisfies the triangle inequality, it is positive, it is non-negative, and is 0 whenever p equal to p hat. So this constraint is essentially saying that let's build a ball inside our function class. This ball is centered at the maximum likelihood estimator. And I'm going to set the radius delta properly such that this ball contains p star. So I'm not going to talk about the details of how to set delta here, but we can set it properly by using the generalization bound of MLE, so that with high probability, this ball is going to contain the ground truth p star. But I don't know where it is, I just know that it contains p star. Okay, so now let's revisit the objective function. So basically the constraint gives me a version space, right? I'm pruning away those function approximators in my function class that I believe are completely wrong, and I'm only going to retain those models inside this ball, which I believe that they potentially could be the ground truth model. But I don't know which one is actually the ground truth model. So now let's revisit the objective function. So in this objective function, as you can see here, for a policy pi, I'm picking the minimum over the function in the function class, subject to this constraint. So in other words, given a policy pi, I'm selecting the least favorable model inside this version space for this policy pi. I'm trying to estimate, what's the least amount of policy value I could get if I can pick the least favorable model inside this version space, right? I'm trying to be very pessimistic for the policy's value. And I can evaluate this policy in this very conservative way for every policy, then I pick the one that has the maximum value. Right, so that's this max mean objective functions do. Good, so let's revisit that tree example, and let's see how this will work. So for simplicity, let's assume that the version space only contains two models. So once I have trained the MLE, I form the constraint somehow magically I have two models left, P1 and P2. Right? I know one of them is going to be the ground truth model, but I don't know which one it is. And let's do the max main objective. Be more specific. So I have P1 and P2. So let's see P1 is equal to the ground truth model. But of course, the learning algorithm doesn't know, right? So let's just pretend P1 equal to the ground truth model, and the P2 is actually the bad model that we just saw before. Right? So P2 is the model that completely messed up the state 3, meaning that it believes that the left action will route you to the right subtree and vice versa. Now from P1 and P2's perspective, they both are consistent with the MLE because I have a huge amount of data on the left subtree. Right? But they just disagree with each other on the right subtree. But they're allowed to disagree with each other because none of them have data support. Right? None of them can prove or disapprove their claims in the right subtree. So now let's see how the conservative policy evaluation works here. So let's evaluate pi star, which is the sequence of right, right, right. So if I evaluate right, right, right in the P1, this will give me reward 1, right? Because I'm going to hit the golden state. But if I evaluate right, right, right in the left subtree, sorry, in P2, because P2 messed up the transition at 3, I will actually be routed to root 13, which is reward 0. So which means that the conservative estimation of pi star's value is actually 0, right? That happens because I'm taking mean over P1 and P2. Now what about the green trajectory? As I said, because we center these models around the maximum likelihood estimator, and the MLE solution will be pretty close to P star because we have infinite amount of data on the left subtree. So which means that P1 and P2, they will be consistent with each other in the left subtree, which means that if we do this conservative estimation of the trajectory left to right to left, both of them will give me value 0.9. Right? Again, P1 and P2, they have to agree on the left subtree because there's just infinite amount of data to support that. Okay, so in this case, the conservative estimation of this suboptimal policy is still 0.9, and our approach will actually pick pi hat instead of, sorry, pi tilde instead of pi star, right? Because 0.9 is bigger than 0. Good. So that seems to make sense. And now let's see some formal claim. Yes.
Sorry, going back to your example.
Yeah.
So the distance between P1 and P2 is exactly the same as the distance would be between P1 and something which messes up the transition from 5 to 10 and 11, based on your delta distance definition before.
Yes.
So in this situation, you could easily get 0 on this part as well, as long as you are really taking distribution with a robust optimization. Clearly, you have something else which tells you that the distance between them has to be measured only on the part of the domain where you have data.
So you're saying that I can mess up the node 5 as well.
Yes.
So
instead of 3.
Yeah. So the thing is that you can't. So imagine, let's assume that you have infinite data on this thing, on the left subtree. All right. So if I have infinite data, the delta, the radius of the ball, I will set it to 0. I can set it to 0, which means that all the survived models, P1 and P2, they have to be consistent with the MLE solution, right? Because the ball is centered at MLE. And they have to be consistent with each other on the training data. But I have infinite training data on 5. My MLE has to be accurate because of the realizability assumption. And because the distance between P1 to MLE and P2 to MLE is 0, P1 and P2, they have to agree on label 5.
So could you go back to your min-max formulation and show what prevents this scenario? Because
That's the constraint. That's the constraint. Yeah, so let me just show the constraint one more time.
Because that's what I missed.
Yeah, so that's the constraint is preventing that. So p hat will be super accurate at state that is covered by the offline data. Right? Set delta to be 0. Set the number of training examples to be infinite. Which means that my survived model P has to agree with my MLE at training examples.
Am I setting delta for individual nodes of your?
No. This is averaged over the training example. So I can set delta to 0 if I have infinite data. So literally the theory supports delta being 0 if I get infinite data.
Okay, maybe I can ask later. I apologize for.
Okay, no problem. Okay, so now let's look at the formal definition of the coverage that I want to talk about. So this quantity looks a bit complicated, but let's look into the numerator and denominator separately. So given a policy pi, this numerator contains the state action distribution induced by my policy pi. And inside the expectation, it is the average model error of a model p hat. Sorry, p prime. And similarly, in the denominator, I have the state action distribution induced by my offline distribution. Right? So I'm looking at the ratio between the average model error under my policy's distribution and the average model error under the offline distribution. And we call this ratio as the coverage. Now let me give you 2 remarks to show that why this coverage kind of makes sense. So the first remark is that this quantity is always upper bounded by the worst case density ratio between these 2 distributions. So picture-wise, think about this case as the distribution induced by the offline policy is absolutely continuous with respect to the distribution induced by my policy pi. So this density ratio quantity is called a concentrability coefficient in RL and has been used in offline RL for almost 15, probably 20 years now. Right, so the density ratio is a little bit easier to interpret because this is just the ratio between 2 distributions that I care about. But as you know, this new definition contains functions in our function class, right? We have p star and p hat. So let's just do the sanity check in the sense that what would happen if my function class contains functions that are exactly equal to p star? So of course, this is an ideal case. This is essentially saying that I have a lot of prior knowledge about my p star. Somehow I can design my function class such that every function in the function class is not too far away from p star. So let's just do the sanity check for that extreme case where every p in the p class is equal to p star. So in this case, the numerator has model error 0, the denominator has model error 0, so 0 over 0 by convention, we just set it to 1. So in this case, my coverage number will be bounded by 1, regardless of the distribution of your pi and offline distribution. They could completely have disjoint support. It doesn't matter. So basically, this new quantity integrates the density ratio concept that has been used in RL for many, many years, and also leverage the structure in our function class together. Okay, so now we can talk about the final background. So with NID offline dataset, with NID offline data points, with high probability, I can learn a policy pi hat that can compete against any policy. So here, V subscript p star superscript pi means the expected total reward of the policy pi measured under the ground truth MDP p star. Right? So this V is the quantity that we care about. So basically it's saying that V hat and V of any comparative policy is upper bounded by the gap of square root 1 over n, where n is a number of examples. So there are a couple of quantities that I want to point out. The first one is the coverage definition that we're talking about. So this is the cost that you're going to pay if you are more interested in comparing against a policy that is less well covered by your offline data. right? So there's a trade-off you need to pay, because there might be a high quality policy that has a very high total reward, but is less well covered by the offline data. So this bound automatically trades that for you. And the second, this is the robustness property, right? In the sense that if there's a policy whose coverage is bounded below infinite, then I can find it with a reasonable amount of samples. And the second part I want to point out is this log of the size of the function class. So here, for simplicity, I just assume the function class is discrete, but it could be exponentially large. So in this case, the log of the size of the function class is a very classic statistical complexity of a function class. So you can replace that by covering number, random Markov complexity, so on and so forth. But the key thing that I want to emphasize here is that this bound has no polynomial dependence on the number of states in action. So you can literally apply it on the infinite MDPs that have the infinite state and the infinite action. And so this is the SL style, the supervised learning style of generalization bound that I was talking about. Okay, so let me give you one example. So far we are talking about very general model setting. Right? Let's specialize a Markovian transition. So this is the non-parametric kernel model where the next state is sampled based on this unknown function f star subject to a Gaussian noise. And let's assume this f star falls into some reproducing kernel Hilbert space that uses the kernel k, where this phi is the corresponding feature mapping induced by this kernel k. Right? So think about this kernel k as an RBF kernel. So somehow we see that our dynamics is embedded in some reproducing kernel Hilbert space as subject to some Gaussian noise. So in this case, we can actually refine that very general coverage condition to this relative condition number. So in the numerator, we have the feature covariance matrix of my policy's distribution. And in the denominator, I have the feature covariance matrix of my off-policy distribution. So in other words, now we are looking at subspaces rather than density ratios, right? So I will call a policy pi that is covered by the offline data if my policy pi only visits some subspace that is covered by the offline distribution. Right? So instead of talking about density ratio, now I'm looking at a subspace, right, in this potentially d-dimensional space. And there are other examples that we demonstrate where you can get very interesting, condition covering number. The coverage definition, including low-rank MDPs, linear mixture models, vector MDPs, and so on and so forth. So I'm not going to dive into the details of these models. So instead, I want to talk about the imitation learning part. Okay, we're going to do some algorithm here, and we're going to look at some experimental results. So traditional imitation learning setting, we have expert demonstrations. We look at the data that is extracted from the demonstrations, state in the demonstration, and the action that is taught by the expert, right? This is a supervised learning data set because I have a state and the corresponding action. Use your favorite supervised learning algorithm, classification, regression, or whatever, you find a policy. It's a super simple algorithm, and this is the famous behavior cloning algorithm. Right? So kind of makes sense. I'm just cloning whatever the expert is doing at the states that the expert visited. Now the issue is that we saw that before, right? We have distribution shift. And maybe in this case, I will have some offline data. So these are the trajectories generated, for instance, by me, who's not an expert driving this car at a high speed. They're not high quality data, but maybe I'm able to use this imperfect offline data to figure out how to recover from mistakes. Right? Maybe I can learn some dynamics from this offline data, and use that I can plan myself back to the expert track whenever I deviate from the expert track. So more formally, we want to consider this setting. I have a lot of offline data pre-collected, they're probably cheap, and I have some very high quality demonstrations collected from a well-trained expert, but maybe the expert is super busy, he or she can only provide 2 demonstrations, so it's kind of expensive to collect more demonstrations. And our job is to figure out if we can combine them so that we can do better than just doing learning on the offline data or just using the expert data. Good. So this is a general framework. So we're going to combine the 2 kind of data sets. and then design an imitation learning algorithm to learn a policy and then deploy the policy. Now let me zoom into this box. I will have two components. The first part is, again, the model fitting. But here I'm going to do a little bit stronger setting. I'm going to learn calibrated model in the sense that I'm going to learn p hat, and I'm also going to learn the uncertainty quantification. So the uncertainty quantification means that for any state action pair, this uncertainty quantification measures the error of my model p hat. Just think about Gaussian process. You know, Gaussian process gives you the mean, which is p hat, and it gives you the band, right? And the bandwidth, the width of the band at any point is the uncertainty quantification. And this is also called epistemic uncertainty, meaning that you will have large uncertainty at places that you don't have training data, and you will have small uncertainty at the places where you have a lot of training data. And with that, we're going to go to the imitation learning framework, where we're going to do this min-max generative adversarial net style imitation learning approach. So here, the max over f, you can think about this f as discriminators that is trying to distinguish the state action pairs from my policy and the expert policy. Right? And your policy is actually the generator that is trying to generate examples that trying to follow the discriminator. Right? Because we don't have online interaction, so we have to do that inside the learn the model p hat. Right? So I'm generating fate to state action pair inside the learn the model, and I'm still trying to follow these discriminators. But because of my models is not accurate, I have to add this epistemic uncertainty. So that's called a penalty. So the penalty will be large at the places where epistemic uncertainty is large, right? So which means I discourage my agent to go to these regions because I don't have training data, so my model is going to be terrible there. But for places where epistemic uncertainty is small, meaning the penalty is small, then I will encourage my agent to go there and try its best to mimic the expert, trying to follow the discriminators there. So let me just quickly explain this idea from this cartoon image. I have 2D space. These blue dots are the states from the offline data. I fit a model, and for models outside this green region, because I don't have data, so the model is terrible, I have large epistemic uncertainty, large penalty. Basically, I'm telling the agent that, hey, you shouldn't go there because there's no data at all. But for the state that falls into this green area, the area that has low uncertainty, we know that we have a lot of data, and our model is accurate, and we have small penalty. So we should encourage the agent to do imitation inside this region. So in some sense, we're doing this trade-off between exploration and imitation. Right, so now let's put the expert into the picture. So let's see the expert trace is covered by this grid. Now this is a particularly nice case because the expert trace is covered by the data. And in this case, our approach can actually do better than just using the expert data. Because imagine that once you deviate from the expert track, you can immediately using the offline data surrounding that area to figure out a way to pull yourself back to the expert track, right? So you're able to correct from a mistake. But of course, there's a worst case where there's no relationship between offline data and the expert data, meaning that your offline data just doesn't cover at all about the expert data. So in that case, there's not much we can do to leverage the offline data, right? The best we could do is just maybe run behavior cloning. So let's see how it works. So we're trying to control this robot without any online interaction. So we train this expert policy, and the expert policy can actually make the robot walk forward in time extremely fast. Let's just collect a few expert demonstrations from this expert policy, and let's just train using this classic famous behavior cloning algorithm. As you can see, the performance is pretty bad, and if you plot the behavior, it looks like this. It will never actually make the robot stand at all, not even walking. And then what we did is that we created a mediocre policy, which we used to generate the offline data. And what we did is that we combined the offline data and the high-quality expert demonstration together, and we trained that policy. So this is what you got. The robot is able to stand and make one step forward, but then it falls down. And when we do our approach, when we combine the offline data and expert demonstration in a more refined way, we can actually learn a reasonably good walking behavior. So we can actually learn to work pretty fast, even though the hand gestures is kind of. Okay, cool. So let me just summarize what I've been talking about. So we went through the process of thinking about the goals of offline reinforcement learning, and basically I emphasize the two properties, generalization and robustness. And for the generalization, what we aim for is something like supervised learning style generalization, right? In the sense that I want to generalize via function approximation instead of memorization or enumeration. And then the robustness is related to the case where the offline data does not have sufficient coverage. So what we can do. So what we said is that maybe we should aim for the best one that is covered by the offline data. So in the ideal case, when the global optimal policy is happen to be covered by the offline data, then we will find it as well. Right? So that's the end, and I'm happy to take any questions. Thank you, everyone.
Time for a few questions.
Yeah.
So you showed us two parts. In the first one, there was data on part of the space, there was no data on the other part. In the second one, there was no data on part of the space, mediocre data on the other, and then expert data on a tiny part of the space, perhaps.
Yeah.
It seems like it can be more finely graded. You could have a confidence level associated with every source of data, some kind of expert ranking, and
Yeah. So
you could put this all together and get an even better.
I agree. So So if you actually have a reasonable amount of expert data, you can actually build this uncertainty quantification on the expert data as well. But the thing is that we only have tiny. So the assumption is that you only have one demonstration, for instance. What are you gonna do?
But what I meant was that your mediocre data may not be uniformly mediocre.
Yeah.
There are mediocre and then mediocre.
Oh, you mean even worse?
Yes.
Yeah. So
you could make it hierarchical.
So we actually did some experiment when we did grade the performance of the mediocre policy, up to the random policy. So the performance is actually getting worse and worse. So this is going to be corresponding to the worst case that I showed, right? Where your offline data does not even overlap with the expert trace, right? Because this is just, at the end of the day, it's just a random policy. The random policy applying on this humanoid robot, never even going to make the robot stand. You keep falling down. Your data set consists of the behaviors of the robot falling down, but your expert consists of state about the robot walking at a super fast speed. So you cannot really leverage any information from that bad data set to infer the walking gait.
I think I might be having trouble explaining what I'm proposing. But let me try one more thing. Suppose between your mediocre level and the expert level, there is an advanced beginner level, and some of your data is labeled that way. Would you be able to take advantage of it?
Yes, I think so. Yeah. So if I combine the mediocre data and the data between the expert and the mediocre, it is possible that my coverage number just improved, right? Because the whole data set probably gets better coverage. It's more related to the expert traces, right? So it potentially get better coverage of the expert traces. Now, of course, this is just my guess. You cannot just infer the coverage by just looking at the performance, right? Because they might be completely different. Like you can go left to reach the goal by avoiding the obstacle in the middle, but you also can go right. But yeah, so it's harder to see how the coverage is measured, but looking at the reward signal might be a surrogate objective function to indicate the coverage.
Thanks.
Sort of related, is it possible to do some kind of hybrid approach where you have offline data and maybe even expert traces, and then you collected data during an experiment and use that as maybe, as you were saying, like a beginner success? If you measured the success of the movements and use that as further input, could you slowly increase your coverage of the space?
Yeah, so are you saying something like, can I do offline plus online?
Yes.
Yeah, so you can do that. There are actually some work trying to do that. So an intuitive way to do that is that you look at the offline data, you look at the coverage of the offline data, right? And then what you can do is actually you can purposely learn to step out of the coverage because you want to collect more data. And then you combine them, you grow your coverage a little bit more, and you repeat, and eventually maybe you explore everywhere. So that's doable too.
Does that help if you don't know, like if you drop the realizability assumption and you don't know your whole state space?
Yeah,
is
so-
that helpful at all?
Yeah, so without the realizability assumption, I think all these pessimism or optimism-based algorithms, they're all going to break.
Okay.
So there's very little work on agnostic learning in RL. That's just very hard. I don't have a good answer about how to do agnostic learning in RL. I wish I had.
Related to realizability, so when you're sort of borrowing this idea from Path, there's the loss function that you use in prediction. It's a bounded loss function. It's just in 0, 1. That you may have an unbounded loss function here. So somewhere in your definition are you encoding the fact that your loss function is bounded? Or?
No. Yeah, so that's a very good question. So the maximum likelihood estimator
Yeah.
has an unbounded range. So you cannot using, for instance, Hofting bound plus union bound to do that. No. So to prove generalization bound for MLE, you have to go through the Hittinger divergence. And then you go to the L1 divergence.
But then, okay, good. So maybe my small worry is in the limit when you have infinite amount of data, you can learn sort of weird pathologies about your model. But for any finite data set and unbounded loss,
Yeah.
it seems like so that guarantee cannot be dependent on the data. It's sort of averaged over all data sets sample.
Yeah.
or
So
something.
so let me just state the generalization bound that you could get for MLE with realizable condition. So you can look at the population L1 total variation distance between your learner model and the ground truth, average over the same distribution. Expectation is the same distribution, and that error will be upper bounded at the rate of 1 over square root of n.
Assuming that the function class is bounded, because total
Yeah. Log of the size of that, for instance, right?
No, and that like total variation only tells you that expectations are close for bounded functions.
No,
If
these are my so these are my densities.
But the
So my
loss-
model is a conditional distribution over the next state, right?
Yeah, okay, let's take this off, right? We'll do some offline learning.
We'll do the last quick questions if we really thank Wen again, and then I'm sure you're happy to hang around and
Yeah,
ask
that will be
questions.
it.
So let's thank Wen again.